This will be the final part of color perception, where we get to discussing the cortex, so cortical processing of color perception, in addition to talking about color constancy, so what happens when the light levels or the illuminant is changing. So that brings us nicely to talking about color in the cortex and this kind of acquired color deficit, because usually what happens, usually the color deficiency, or the color deficiency that we have because of defects or absences of cones, we are born with those deficiencies. But typically the way an achromatopsia occurs is we have some kind of brain damage. And a lot of times this is brain damage due to stroke. But again, Mr. I had a car wreck, so it depends on how the brain damage occurs. Cerebral achromatopsia, A meaning not, right? So a world without color or not having color is a monochromatic world due to damage in the cortex. So, and remember, the cortex, the cerebral cortex, is that outer layering of the brain, so more easily damaged than by trauma than subcortical structures. These people appear to still have some experience with wavelength, but not in the form of color perception. And the question is here, is it really more enhanced sense of differences in gray? What do we know about color in the cortex? I actually had my brain and behavior class this year read a different cerebral achromatopsia article where they were trying to figure out exactly what's damaged and what is V4 and V4 alpha and what does this mean for our perception of color. Well, the overall answer is we don't know much. I mean, we know some things, but they don't add together into some nice, clear answers. We know that there's no single module for color vision, that we are seeing cells that are responding to color all the way from those retinal ganglion cells through the lateral geniculate nucleus to V1 to V4, and they help us with, they go into the inferior temporal cortex to help us understand what objects are, but there's not a single module for color vision. We know that some cortical neurons are responding to just certain wavelengths. I actually had a great conversation in my honors class where the person was talking about P cells, M cells, and K cells, where those K cells are responding to shorter wavelengths, and the P cells, it looks like not so much, which is going to influence subcortical neurons and cortical neurons and what they are responding to. In many areas of the cortex, including V1 and the ventral stream, so where we are doing our object recognition, we have some neurons that have opponent processes. So we saw this in the last bunch of slides of the red, green, blue, yellow opponent processes. Those continue through the cortex. And we know that neurons that respond to color also respond to form and orientation. As we are going into that what pathway and figuring out what objects are, color helps us with that. I often also, at some point in all of this, usually have somebody else who is extremely myopic in my classes and mention something like, and if you are extremely myopic and the world is completely blurry when you take off your glasses, raise your hand if you know how much you use your color vision. So red lights and green lights really stand out to me. What I see with the McDonald's sign is just yellow and red. And it lets me know that that's a McDonald's sign, even though I cannot see the giant M. Okay, those colors help us to understand what objects are. What do we know about color in the cortex? We know that it is very distributed processing. So this is a study that was done in 2010, where they asked participants whether or not two blobs were the same or different, depending on texture. You can really see it in the first one, but the texture is different. Color or shape. Okay, and what we can see in the brain imaging there is the activity in response to texture. We see that back in the back of the occipital lobe. color, we see the green kind of already, just the green, when I'm just responding to color, is kind of distributed up there. The red must be going into the inferotemporal cortex when we were dealing with shape. The yellow, okay, what the yellow is responding to all three, or color and anything else. And so you can really see, if you put the green and the yellow together, you can really see how distributed color processing is. And so I asked the question here, this is one of those questions I don't expect a student to have an answer to, is how does cortical damage cause achromatopsia? Because, right, if it's really distributed, then how can a specific brain damage cause a loss of color? Well, if you read the article on achromatopsia, which was just one of the choices, it's complicated. And what aspects of color vision those people are losing, even that's complicated. Is it memory for colors? Is it memory for colors of specific objects that I'm used to seeing in a particular color? Is it color constancy? Is it color but not wavelength? It's all really very complicated, and it's very distributed, and rarely is it a situation where we've lost all of that stuff. And if we've lost all of that stuff, we've usually lost other aspects of the inferotemporal, that pathway. And we've lost some of our, usually it's prosopagnosia, and we've lost our facial recognition in addition to the processing of color. And so some of that subcortical and V1 kind of processing of color is still occurring, is just not getting up into the kind of conscious perception of color, if that makes sense. So some questions that we might ask ourselves at this point as to differentiate some of this is, where is information about wavelength processed? Because I'm going to talk about MS here, who has damage to the cortex, has cerebral achromatopsia, but the photoreceptors are still intact, and MS can still use wavelength information. He appears to be able to detect the line separating two adjacent fields of different colors of different wavelengths, and that's why I have on a previous slide that kind of in brackets this, are they differentiated? Is it more sensitivity to differences in gray? Because it's still going to be harder to pick blackberries and do that kind of stuff, but wavelength information can be maintained when we lose our ability to see color. And then a separate question then is where is the perception of color, the actual experience of color, determined? So when we talk about color constancy, there's a question of how do we see the world as having a basic color constancy, because when we're out in different illuminants, or we come inside to different illuminants, then those illuminants are emitting different wavelengths of light. What I'm showing there in figure A is that when we are out in the sunlight, that is basically emitting across the electromagnetic spectrum, right? Because that's what's going through the prism or the water to become refracted into the rainbow. That's across the electromagnetic spectrum. If we go inside and we're in these new LED lights, what's mostly being emitted is the shorter wavelength lights. There's some bits of longer wavelengths, but really the majority is these short wavelength lights. And then if we go into lighting where there's incandescent lights, or the tungsten lights, then what they are emitting are those longer wavelengths of light. And so when I have on clothing, or if I look at someone's eyes or hair, all of that is going to be absorbing some wavelengths and reflecting some wavelengths, but that can be shifted around depending on the illuminant. So a green sweater outside under sunlight, though, it appears green, and then when the person comes inside, it still appears green, even though now the reflectance curve has really been shifted or changed. If we look at the reflectance of, let's say, a green shirt, basically, remember, we're not just right at 500 nanometers or 510 nanometers, we are reflecting some of the wavelengths around that in a kind of normalish looking curve, not really, but a little bit. And if we are in the sunlight, okay, that is going to be the basic reflectance curve, because what's hitting me is across the electromagnetic spectrum, and I am reflecting what I am reflecting of that spectrum and absorbing other pieces. But then if I go into the LED lights like we did before, that's going to be shifted down. So if we look at the figure in C, that's shifted down, and that could have a more, could become more blue if that was the way it worked. But instead we have this color constancy where we still see green. If we go into the incandescent lights, or the tungsten filaments, that gets shifted up. That could be that reflectance curve that you're seeing in the orange there in C. That looks more like yellow, but we're going to see green, and green is really different from blue and yellow, and yet we still are going to perceive the green shirt as green, even though it has these different amounts of reflected wavelengths in these different contexts. So it looks like part of the answer to this is what's called chromatic adaptation. So they did a study back in 1989, Uchikawa and colleagues, where the person would be looking at a green paper, and the green paper would be under a basic white light, and then they also had the person's eye under the basic white light. And what you can see from what they're saying there is that the paper still appears green at that point. If what they do instead is they put the green paper under a red light, but the light, the person's eye is still under a white light, then we see a shift of that color to appear more reddish. And so it has been shifted to the longer wavelength lights, or the longer wavelengths. If now we put the person under a red light along with the green paper under the red light, now we see a slight shift, maybe appears a little bit more yellowish, but it doesn't have quite the same shift as we saw in B when the person's eye was under the white light. And so what's happening there is we're having an adaptation to the color of the illuminant, or the wavelengths of the illuminant, and that is compensating and decreasing sensitivity to particular wavelengths. So that gives us partial color constancy. That's part of the answer, but you can see that even in C there, that there is some shift towards more yellowish. And again, that's not what's happening when we walk from outside to inside, and we're seeing people, their clothes don't change color or shift color. So that's just part of the answer. And there are some additional explanations. This is actually a pretty complicated thing that we do. One is that the surrounding environment is really important. I have a question mark there, and I used to ask more questions here, but I've kind of lost my questions. Plus, there's no one to talk to except this screen, so it's not as fun. But we can ask ourselves that, so when we are, part of what's happening is, according to Retnek's theory, is that the cortex is really comparing the different information that's coming from different parts of the retina, and it's more comparative. So the surrounding environment is really important, and you can see these blocks, the blue, yellow, and red, and then the light blue over on the left. And if we see those under different illuminants, that they can to some extent change slightly, but to some extent too, we're getting information about what color that is based on the other colors in its environment. And this is even without, these are even objects that are meaningless to us, where we wouldn't know the color. So I'm also going to talk about memory for color just a bit as we go back to, if you remember that study where people recognized the yellow bananas faster than they recognized the purple bananas. So there's also this aspect of memory for color that is influencing our color vision. And there was a similar study to that as people looked at, and I'm going to use bananas again because I can't remember what fruits and vegetables they used, but so if they give gray bananas on a gray background, people still perceive them as being slightly yellow. So our memory for color really is influencing our perception of objects. And if we put all of that together, that results in a kind of color constancy. It really takes the chromatic adaptation, the comparisons with the surrounding environment and what's on the retina, and then also memory for color for us to get this nice, rich sense of color constancy where things just aren't changing depending on the illuminant. So I'm going to end here today. This is the final part of color perception, and I am skipping lightness constancy this time around, but it was kind of a short thing that I think is okay to skip, and everything else hangs together just fine. I'm ending up with this screen that I told you these questions that I was going to come back to. First, I do want to say this reminder of how color perception is a psychological phenomenon. It is our interpretation of the physics of the world that is basically wavelength information, and that color does not exist out in the world. And when we start to talk about things like how much a particular color is influenced by context, like what we saw with Joseph Albers' artwork, or how we have this color constancy, it becomes more and more clear, I think, that this is the psychological interpretation, and that even without maybe missing a cone or having some real difference that's clear, and that we're going to be clearly different in our perception of color, whether or not we are experiencing the same red. When I point to this pillow and say, yes, that's the color red, and you agree with me that that's what we have learned to call that color, and we're pointing to something out in the world, but whether we're truly perceiving that red, experiencing that red the same, or even, well, I'm not going to say even similarly, I'm sure we're experiencing it similarly, but whether we're experiencing that in the same way is not clear. And it's interesting how, I think it's your author who brings up how different people have different favorite colors, and I think it is blue that is most commonly a person's favorite color. And what we have kind of connected to colors, each of us, is while there is a great deal of overlap that could potentially be linguistic from our language, but then there's some that's maybe appears to be more cross-linguistic, that how much sort of emotion and feeling is brought up by color is another kind of question. So I have these questions. What does color vision do for us? What physical attributes of the object influence its perceived color? What physical attributes of an object's environment influence its perceived color? And then finally, how can we describe color experience? Where those first three, I think we'll talk about pretty quickly. So we'll go through these on Monday, but really think about how you would describe your color experience. As I've tried to share some of mine with you, being myopic, how much I use color, especially when I can't see and everything's blurry, how much that tells me about objects, but also that, so matching colors is not something I do very well. I don't seem to see the variations in colors or how they should be going together or not very well. And all of us have a really, I think, unique experience with color that when we talk about it with each other, we can learn from. So think about how you might describe your color vision experience to somebody who either doesn't experience color, or to somebody who doesn't experience vision at all, how you would explain and describe your experience. And we'll just do this one slide to finish up color vision on Monday.